Hi, my name is Zmolikova, and in this presentation, I will introduce BUT system for CHiME 6 challenge, where BUT stands for Brno University of Technology. I will right away show an overview of our results. We have submitted systems to both tracks. Here in this plot, you can see a rough breakdown of the results into different parts of the systems that we modified. All of the results in blue are on development set, and the final ones also on evaluation set. For track 1, we introduced some improvements on both acoustic and language modeling parts of the system, and on track 2, we additionally used our own diarization and also modified the enhancement. You can already see here that we have a bit of discrepancy between the results on def and eval on track 2, which I will address later in the presentation. Our system for both tracks are very similar, so I will describe both at once in the presentation. Only the diarization and enhancement parts will regard track 2 only, and in other cases, I will explicitly state when there is a difference. Let's start with the diarization. For this part, we have used our diarization based on Bayesian hidden Markov models with variational bias inference. We use this model to cluster X vectors, which is why we call it BBX. In this method, we model the speaker activity with hidden Markov model with states corresponding to speakers. So the transitions between the states correspond to the speaker turns. This model does not consider speaker overlap. It assumes that one frame belongs to one speaker only, which for CHiME data is not so much true, but it is a simplification we make. And on next slide, I will also show some post-processing, which allows us to label also some of the overlap. The state distributions in the HMM are modeled by PLDA, which is trained on the CHiME training data. This PLDA and also X vector extractor and speech activity detector are taken from the baseline system. One difference to the baseline system is that we have extracted the X vectors more finely. We have extracted 4 X vectors per second, which is, I think, 3 times more than what was used in the baseline system. The results presented here are on the depth set evaluated with the diarization metrics. You can see improvements here on both DER and JER of about 10 and 20 points. And this is compared to the baseline system, which uses agglomerative hierarchical clustering. We further fine-tune this diarization by applying enhancement and then running the diarization again on the enhanced data. The baseline system in track 2 used beamformat as enhancement, but already from the previous challenge, we know that guided source separation from Paderborn works significantly better. So we apply GSS here, and we use the outputs of our diarization as the guidance that GSS needs. The GSS frontend enhances all of the speakers according to the diarization. So on the output of GSS, there are 4 recordings with 1 speaker enhanced in each. We run the diarization again on each of these 4 recordings, but then we keep only 1 speaker from each, the enhanced speaker. Looking at the image, which we have here, if the speech activity detection detects a speech segment, then our diarization assigns this segment to, let's say, 2 speakers, speaker A and speaker B. If we run GSS using this diarization, then we get 2 recordings, one with speaker B enhanced and one with speaker A enhanced. We then run VBX again on these 2 recordings but we keep only speaker B from first and speaker A from the second. By combining the outputs like this, we can also detect some of the overlapped parts. It may, however, also happen that some part which was originally labeled as speech is now not assigned to any speaker. In this case, we just copy the labels from our original diarization. This is then what the final diarization looks like. You can see here that this further post-processing of the diarization brings further improvement on the diarization metrics. And later we have also seen that these improvements translate to the ASR performance. However, as I have mentioned already in the introduction slide, we had quite a difference between def and eval performance, which stems from the diarization. On eval set, the improvement on JER is slight from using VBX, and on DER, VBX even hurts the performance. Our suspicion of why this happens is that on the evaluation set, there is a bigger portion of silence, and also the speech activity detection has quite high false alarm rate. This means that a lot of the silence needs to be included in the speaker models in our diarization model, which can be detrimental. This could be addressed in the model, for example, by introducing a silence class, but we haven't explored this direction since these problems didn't show up on the development set. We will now explore this more when we can allow ourselves to look also at the evaluation set. Next part of the systems that we explored is acoustic modeling. And the first aspect that we looked into is which data to train on. In all of the experiments that I show here, we included enhanced training data, where enhanced is using GSS to make the training data more matched to the test data. In addition, we added warn data, either from one of the microphone or both of the microphones, then the warn data with artificial reverberation, and also part of the far field data from the Kinects. From the Kinect data, we have only selected utterances from the non-overlapped parts. Looking at the results, these are word error rates on def. Increasing the amount of warn data by using both microphones is helpful, and further adding more reverberation and far field data still improves the results. However, our conclusion from these results was that warn plus enhanced is already enough, because looking at the sizes of the datasets, there is quite a small improvement for the price of making the data much larger. These conclusions are more or less similar to what was published by people from Toshiba in 2019. Next, we looked at the architecture and the training of the acoustic model. Here we have two very straightforward improvements. First is by replacing the baseline TDNNF by CNN TDNNF, which I would say consistently improved the results over our different experiments. Also, using the sequence discriminative training with SMPR on top of LFMMI further decreases the error. Here the results that I'm showing on track 2 are already quite better than the baseline, because in these experiments we already use our diarization and the modified enhancement. Staying still with the acoustic modeling, there are two more modifications we used in our final systems, which are making use of the voxel data and also exploring speaker adaptation with eye vectors. For the first one, in second track, we were allowed to use voxel dataset. However, this data don't have any transcriptions. What we did is that we used system trained on CHiME to transcribe part of the data and then added this transcribed voxel data into our training. We have quite a good previous experience with such semi-supervised training, but usually the case where we would use this is when we have labeled out-of-domain data and unlabeled in-domain data. So the semi-supervised training is usually a way to adapt the system towards the target domain. While here the situation is quite opposite, the unlabeled data are the out-of-domain. Still, though, the CHiME dataset is not so large and the speaker variability in the training set is not so high, so including the additional data in the training can be helpful. And we can see these on the results, where using the voxel dataset does bring improvements. I don't have this in the presentation, but we have seen similar trends also in end-to-end ASR systems, where some unsupervised pre-training with voxel data helped the systems. The second improvement presented here is from fine-tuning of the I-vectors used in the system. In the baseline system, there are I-vectors used for speaker adaptation, which are extracted in online fashion during training. And for the test time, the Calde recipe always breaks the speakers into several subspeakers to extract the I-vectors. Our thinking here was that for this dataset, it might be particularly important to have good I-vectors, because when there is overlap, it is important for the system to know which speaker to transcribe. We kept the original online I-vectors in, and we concatenated them with hopefully more robust I-vectors, which are either estimated from all of the speaker data from the entire session, or only from the non-overlapped parts of that speaker. The results here should be compared to the first row, and both of these options bring some improvement, where the non-overlapped I-vectors are slightly better. In this slide, there are two systems which are specific to only one of the tracks. The last presented with the non-overlapped I-vectors is used only for track 1, because we used annotations to detect the non-overlapped parts, and the system with voxel is used only for track 2. Next area of our explorations was language modeling. The baseline system used trigram language model, which we interpolated with LSTM language model. We used this model to rescore N-best hypothesis with N3000. And apart from this classic NN-based language model, we introduced two other improvements. First, since we have the entire sessions available, we thought that it might be useful to include the context of the conversation. So we transferred the hidden state of the LSTM over the segments. And second, since the text corpora of CHiME is quite unusually small for language modeling, we have also explored regularization techniques. Apart from the standard dropout, we have also randomly replaced some of the input tokens into the model with rate 0.3. The LSTM model itself leads to about 1% improvement in word rate, and the additional improvements further bring it down by another 1%. Finally, we fused multiple models. We used rover fusion over different acoustic models, so in all of them, diarization and enhancement is kept the same, only the acoustic models differ. We used 7 systems for track 1 and 8 systems for track 2. You can look into the paper for more details, but they are basically the systems which you have seen previously in these slides. Here in this plot, you can see the difference between the single best systems and the fused systems for all of the categories. With this, I would like to conclude the presentation. You can again see here our final results of all the categories on both development and evaluation sets. Our improvements compared to the baseline come from diarization, some improvements in acoustic modeling and language modeling. As a final note, I would like to thank the organizers of the challenge for creating this data set and all the baseline systems and organizing the challenge overall. And eventually, I will be happy to hear and answer all questions about our system during the workshop.